Welcome back, everyone, to The Deep Dive. Today we are diving into a really big question. What is mathematics, really?
A big question indeed.
So to tackle that, we are going to look at one philosophical view called deductivism. And as you know, on The Deep Dive, we like to unpack really dense, really potentially confusing topics and give you that shortcut to being well-informed.
Yeah, hopefully with a few aha moments along the way.
Exactly. So deductivism, this is a view that says math is not really about numbers or shapes
Right,
themselves,
it's not about these objects.
but about something else entirely.
Yeah, it gives a very different answer to that question. What makes a mathematical statement true?
Hmm. Okay, so let's get into the specifics. Let's think about 2 plus 2 equals 4. Now, most people just kind of take that for granted as like, yeah, that's just how arithmetic works. But the deductivist has a very different perspective on it.
Totally. They would say that it's not true because it accurately describes some reality about numbers out there. It's true because the sentence 2 plus 2 equals 4 follows from a set of starting points that we've agreed on.
Okay, so it's like we've all decided on the rules of the game.
Yeah, we call those the axioms,
Oh, yeah.
like the fundamental building blocks of the system. And from those, you can logically deduce 2 plus 2 equals 4.
Okay, so the truth comes from following the rules rather than from the numbers themselves having some kind of inherent property.
Exactly.
So is the same thing true for something like 2 is prime?
Absolutely. Again, it's not that the number 2 has this mystical primeness about it.
Right.
It's that the sentence 2 is prime can be derived through logic from those axioms.
Mhm.
And what's really interesting is that deductivists think this applies not just to simple arithmetic, but to all areas of math.
So even very complex, high-level math.
Even stuff that seems way more abstract, like take a statement from group theory, something like, every group G has exactly one identity element.
Okay, yeah, I vaguely remember that from university math.
The deductivist wouldn't say this is true because of some mysterious property shared by every abstract group out there.
Yep.
They'd argue that it's true because that sentence can be rigorously deduced from those axioms that define what a group is.
Got it. So the big idea is that all mathematical truths, no matter how simple or complex, can be reduced to this form. They follow from the axioms.
Exactly.
So math is almost like a game of logic, then, played on the foundation of these axioms.
In a way, yes. It's about exploring the logical consequences of our starting assumptions.
It makes it feel less about discovering hidden truths and more about exploring what must be true if we accept those initial rules.
That's a great way to put it. And for anyone who finds the idea of these abstract mathematical objects a bit spooky, deductivism offers a way to sidestep that whole issue.
Yeah, it's not about whether numbers or sets really exist. It's about what we can rigorously derive from our starting points.
Exactly. And, this wasn't just some fringe theory cooked up by a few philosophers. Deductivism had a real following in the late 19th and early 20th centuries.
Big names in mathematics were really drawn to this view, and it's had a lasting influence on some modern perspectives, like structuralism, which also emphasizes the importance of those axiomatic structures.
That's super interesting. So we have a lot of ground to cover.
We do.
Our mission for this deep dive is to really unpack the core ideas of deductivism. What motivated these thinkers to see math this way?
Yeah, the motivations are really important.
Then we'll dig into the contributions of some key figures historically. And of course, we need to look at the big challenges that deductivism faces.
Because no philosophical view comes without its critics.
Of course. And that's how we get a deeper understanding. So let's start with one of the titans who championed deductivism, Bertrand Russell. His book, The Principles of Mathematics.
Oh, yes, a classic.
Starts with a really bold statement that kind of sums up the deductivist spirit.
It really does. Right in the first sentence, he says, pure mathematics is the class of all propositions of the form E implies Q. And he even goes to what seems like extreme lengths to fit even basic equations like 1 plus 1 equals 2 into this if P then Q mold. He says something like, if X is 1 and Y is 1 and X differs from Y, then X and Y are 2. Why make things so complicated? Why not just accept 1 plus 1 equals 2 as a simple fact?
Well, Russell's goal was to really expose what he believed was the underlying logical structure of all mathematical statements. By introducing variables, he tried to show that even basic arithmetic could be expressed as implications. He was aiming for absolute certainty in math by rooting it in logic.
But I can see why some philosophers say this makes him more of a structuralist, right? I mean, Putnam, for instance, interpreted Russell as saying that if a certain structure satisfies some axioms, then it must also satisfy certain theorems.
You're right, that does sound very structuralist, but when you look at Russell's writing, there's a very strong emphasis on deduction.
Okay.
He repeatedly says, all mathematics can be strictly and formally deduced from logical principles.
So the focus for Russell was on the process of deduction, not just the structure.
Exactly. And for him, logical implication was fundamentally a deductive relationship. So I think the evidence points to Russell as a deductivist, even though those categories might have been fuzzier back then.
Okay, that clears up Russell's place in all this. Now, what about another giant of that era, David Hilbert? Where did his ideas fit into the deductivist picture?
Hilbert definitely had what we'd call his deductivist period, especially around the turn of the 20th century. He was really impressed by how successful axioms were in geometry.
Yeah, like Euclid's axioms.
Exactly. And he wanted to apply that same rigorous approach to the concept of number, to give it final presentation and logical certainty, as he put it. He wasn't a fan of the more informal, ad hoc ways math was often done.
So his goal was to lay down those fundamental axioms for numbers, just like Euclid did for geometry.
Precisely. He even came up with a specific set of axioms for the real numbers, 18 of them, actually.
18.
18 axioms. One example is that from the number a and the number b results through addition a specific number c, formally. A plus b equals c, or c equals a plus b.
Okay, that makes sense. And from those axioms, you can supposedly deduce all sorts of truths about real numbers.
Exactly. And Hilbert insisted that any proposition about real numbers was only valid if it could be proven from those axioms in a finite number of logical steps.
Sounds very much in line with deductivism.
Absolutely.
Yeah.
And this idea that any mathematical problem can be solved with a finite number of deductions was a big theme for Hilbert. He even talked about this in his famous mathematical problems lecture. But here's where things get interesting. He also had some ideas that we now recognize as early structuralism. He talked about thinking of a system of objects that satisfy those axioms. And he used this famous example, which he got from Pasch, about replacing geometric terms with everyday objects. Like instead of points, lines, and planes, you could have tables, chairs, and beer mugs. As long as those objects satisfy the relationships defined by the axioms, the theorems would still hold true.
So it didn't matter what the objects actually were, just how they related to each other within the axiomatic system.
Exactly. So that's definitely leaning towards structuralism. And Hilbert kind of bridged these two ideas, deductivism and this early structuralism, with his completeness assumption. He believed that if a set of axioms is consistent, meaning it doesn't lead to any contradictions, then there must exist some system of objects that actually satisfies those axioms.
Oh, so consistency guaranteed existence in his view.
Yeah, though that relied on assuming we could always have complete and consistent axioms for all of mathematics. But there's another interesting difference between Hilbert's deductivism and Russell's. Remember how Russell, with his logicism, wanted to define all mathematical terms using only logic?
Yeah, like getting rid of number and set and replacing them with pure logic.
Right. Hilbert didn't go that far. He accepted certain non-logical terms, like the symbols for numbers, as primitive. They were basic building blocks, but they didn't need to be defined in terms of something else. What mattered was their role in the axioms and the relationships they had within the system.
Okay, so Hilbert's deductivism was kind of its own flavor. And speaking of different flavors, we also need to talk about Moritz Pasch, who had his own perspective on all this.
Yeah, Pasch was really interesting.
The entry talks about his work on axiomatizing geometry in 1882. What was his take on deductivism?
Well, he was really insistent that deduction should be totally independent of any meaning we associate with geometric terms or even any diagrams.
So, like, you can't rely on your intuitive understanding of line or point.
Right, or on any pictures. He believed the proof should be purely about the logical relationships between the terms as they're defined in the axioms. If you needed to appeal to meaning or a picture, that meant there was a gap in the logic, or maybe the axioms were flawed.
So for him, it was all about that pure, formal, logical deduction. Nothing else mattered.
Exactly, and he even distinguished between what he called the properly mathematical part of a theory, which was all about rigorous deduction, and the pre-mathematical part, which was where you introduced the basic concepts and axioms.
And how did that relate to what we were just talking about with Hilbert and the importance of consistency?
Well, while Hilbert saw consistency as the key criterion for a good set of axioms, meaning they shouldn't lead to contradictions, Pasch had this interesting empiricist view.
Empirical.
Yeah, he thought those axioms should have some kind of independent grounding in our experience of the real world. He even distinguished between what he called real mathematics, which had this connection to reality, and what he called hypothetical geometry, which could be logically consistent, but had no tie to the real world.
Interesting. So it wasn't enough for the axioms to be logically sound. They also needed some connection to our experience of reality.
For Pash, yes. And that was quite a unique perspective.
It was. Now, let's jump ahead a bit in time to Haskell Curry, who offered a more modern take on deductivism after Gödel's incompleteness theorems kind of shook things up.
Right. Those theorems had huge implications for math.
So how did that affect Curry's view?
Well, he fully acknowledged that Gödel showed the limitations of formal systems. We can't have a single system that captures all of mathematics. And he emphasized that the specific axioms you choose are kind of arbitrary. Different systems can be equally valid, structurally speaking. For him, the essence of math wasn't in any particular system, but in the study of formal structure itself.
And he called his view formalism, right. But the entry says it's actually very much in line with deductivism.
Yeah, that's because some people see formalism as saying that math is just a meaningless game with symbols. But Curry rejected that. He insisted that math does have truth conditions,
Okay.
and that the only way to go from one statement to another is through valid logical inference. He even talked about an objective criterion of truth within a formal system. For him, a formal system wasn't a game, it was a body of propositions.
Got it. So his formalism was still very much about deduction and logical consequence.
Exactly. And his motivation was to have a philosophy of math that was free from metaphysical bias, as he put it. He wanted to avoid any commitment to the existence of those mysterious, abstract mathematical objects.
Interesting. So one final historical figure we should touch on is Brouwer and his intuitionistic view of mathematics. Both deductivism and intuitionism seem to put a lot of emphasis on proof, so where do they diverge?
That's a great question, because on the surface, they might seem similar. Curry himself even said that if you take away the metaphysics from intuitionism, the differences might disappear. But Brouwer's intuitionism is actually radically different from deductivism. He rejected the whole idea of mathematics being about axioms.
Whoa, he rejected axioms entirely.
Yeah, he even called axioms illusory. He believed the ultimate standard of mathematical truth wasn't deduction, but the actual mental activity of constructing mathematical objects and proofs.
So for an intuitionist, math isn't something you derive from rules, it's something you create in your mind.
Exactly. And Brouwer really separated mathematics, the mental activity, from any language or symbols we use to represent it. He said no formal system could fully capture that dynamic, creative process.
So that's a big contrast to deductivism, which relies heavily on formal systems and deduction rules.
It is, but it's also interesting that both views move away from this traditional realist picture of mathematical truth. They both offer what we might call a verification-based account. So for deductivists, it's proof within a formal system that matters. For intuitionists, it's that mental construction. But neither is saying that mathematical statements are true because they describe some independent reality.
Okay, I see. So both focus on how we verify math, but through very different means.
Exactly. Oh, and just to clarify, deductivism doesn't have to be tied to classical logic. You could have deductivism based on intuitionistic logic, too.
Right. That makes sense. So we've laid out the historical background of deductivism and some of its key figures. Now, let's get into the hard part. The challenges.
The critiques.
The critiques. The first one the entry highlights is that meaning matters.
Right. This is a big one.
What's the core of this objection?
It's all about the question of whether deductivism really captures what we mean when we make a mathematical statement. So a deductivist says that P is true if and only if it follows from the axioms, right?
Right.
But are they really capturing the ordinary meaning of P, or are they just giving a philosophical reinterpretation that might be quite different from how we intuitively understand those statements?
Like when I say 2 + 2 = 4, I'm probably not thinking, oh, this follows from Peano's axioms.
Exactly. And the problem goes deeper than just whole sentences. Deductivism also has to account for the meaning of individual words and symbols. Like, what does 2 mean in this framework, or prime? Their word-level semantics have to fit with this overall idea of deducibility.
Right. And we use math in all sorts of ways, not just asserting truths. We doubt, we question, we wonder if something's true. How does all that fit into this deductivist picture?
Exactly. It's not always as simple as just saying, we are asserting that this follows from the axioms. That might not capture the full complexity of what we're doing with mathematical language.
The entry also brings up proof by assumption, which is such a common technique in math.
Yeah.
How did that work with deductivism?
It gets tricky. A lot of proofs involve temporarily assuming a statement to be true and then seeing what follows. If you get a contradiction, you know the original assumption must be false.
Yeah. Classic proof by
Yeah,
contradiction.
right. But for deductivism, the question is whether assuming P is the same as assuming that P is derivable from the axioms. The example they give is an odd perfect number.
Okay.
If you assume M is an odd perfect number, does that mean you're assuming the axioms prove that?
Hmm. Right.
It gets into some subtle issues about how you interpret those assumptions. Maybe you're temporarily adding P to the set of axioms, but then you have to be careful about what consequences you can draw from that.
And what about Parsons' distinction between reflexive and unreflexive deductivism? How does that relate to the meaning of mathematical statements?
Parsons pointed out that the reflexive view, where you interpret a statement like 2 plus 2 equals 4, as being about its own derivability from the axioms. Well, that seems a bit strange. Do we really mean that when we talk about math?
It does seem like we're adding an extra layer of meaning that isn't really there in everyday math.
Right. So he proposed this unreflexive view, where the statement is more like, if the axioms were true, then this would be true. But as the entry points out, the reflexive form is often preferred to avoid problems with infinite axiom sets.
Right, you don't want to end up with infinitely long sentences just to express something simple.
Exactly. So even defining what deductivism means is a challenge.
So much for a simple and straightforward view of mathematics.
Right. There are layers to unpack.
Okay, so meaning is a big hurdle. The second challenge focuses on provability, to reify or not to reify. What is this all about?
Well, since provability is at the heart of deductivism, the idea that math is about what can be proven from axioms, we need to be clear about what provable actually means.
Okay.
The big question is whether provable means there actually exists a proof, like a concrete sequence of steps, or if it's a more fundamental concept that doesn't rely on proof objects.
So the first option is to reify provability, to treat it as the existence of these proof objects.
Right. The most natural way to think about a proof is as a series of sentences, starting with axioms and ending with the statement you're proving. But a lot of proofs are so long and complicated, it's hard to think of them as just physical objects written down.
Right, they seem more like abstract structures.
Exactly. So if a deductivist goes this route, they're likely committed to the existence of abstract linguistic objects, proofs as abstract entities.
But wasn't the whole point of deductivism to avoid believing in abstract objects?
Well, that was one motivation. But now you have to believe in abstract proofs. And some philosophers argue that if you're okay with abstract linguistic objects, why not abstract mathematical objects too?
That's a good point. So to avoid this commitment to abstract proof objects, some deductivists take a non-reifying approach.
Exactly. And this often involves using modal logic, where you treat notions like necessity and possibility as fundamental.
Okay.
So instead of saying P is provable, they might say, it's logically necessary that if the axioms are true, then P is true. Hartree Field is a good example of this kind of approach.
So you shift from talking about proofs to talking about what's logically possible or necessary.
Right. But these modal accounts haven't been widely accepted by logicians. There are concerns about how much they can express and whether they really avoid bringing in mathematical concepts through the back door.
So even defining what provable means turns out to be a philosophical minefield for deductivists.
Definitely. It's more complicated than it first appears.
Okay, the next challenge is a big one, especially for a view that puts so much emphasis on axioms. Unaxiomatic mathematics.
Right. How can deductivism account for all the math that was done before anyone even talked about axioms?
Yeah, like the ancient Babylonians had incredibly sophisticated mathematics, but not in the form of formal axiomatic systems. And even in modern times, a lot of mathematical progress happens through methods that aren't strictly deductive, like Euler's work, which was often based on intuition, analogy, and just trying things out.
That's a valid point. But a deductivist could argue that even when axioms weren't explicitly stated, there were still underlying principles at play. Any consistently used mathematical method or result implies some set of assumptions, even if they're not formally spelled out. It's like a tacit set of axioms. And even methods that aren't axiomatic or deductive can still lead to knowledge if they reliably track what could be formally proven.
So like the Babylonians didn't have a formal system for solving quadratic equations, but their methods consistently gave the right answers.
Exactly. It suggests they were tapping into some underlying mathematical truths that could later be formalized. And the same goes for Euler, whose methods, though not always rigorous, often led to correct results.
So maybe deduction is happening behind the scenes, even when it's not explicit.
That's one way for a deductivist to handle these cases.
But the next challenge, a regress, sounds like it goes even deeper and could really undermine the whole project.
It's a clever argument. It asks whether the deductivist interpretation should apply to statements about deduction themselves.
Okay, now we're getting really meta.
We are. So let's say 2 plus 2 equals 4 is interpreted as the sentence 2 plus 2 equals 4 follows from the axioms.
Okay.
Shouldn't that statement also be subject to a deductivist interpretation?
I see where this is going.
It's like an infinite loop. You'd end up saying the sentence 2 plus 2 equals 4 follows from the axioms, follows from some other axioms, and so on forever.
It's like those Russian nesting dolls.
Yeah.
But with infinite layers of interpretation.
Exactly. Even the simplest statement becomes infinitely complex.
So how can a deductivist escape this regress?
They'd probably say that claims about deduction are not mathematical facts in the same way that requires a deductivist interpretation. They're more like foundational facts about logic itself. We might use math to analyze these systems, but the basic fact that something follows from something else is just a feature of how logic works. It's like the difference between a meteor landing, which is a physical event, and the mathematical calculations we use to predict it. The calculations are math, but the landing itself is not.
So the fact that a conclusion follows from premises is not itself a mathematical fact that needs further interpretation.
Exactly. It's a kind of meta-level truth about deduction itself.
Okay, I think I'm starting to wrap my head around that.
It's a tricky concept.
It is. Okay, let's move on to another big one. Applications. If math is just about deductions from axioms, how do we explain why it's so incredibly useful in describing and predicting the real world?
This is a challenge for a lot of philosophies of math, not just deductivism. It seems almost magical that this abstract stuff works so well to describe the physical world. Deductivism seems to have an easy answer. If a physical system satisfies the axioms, then the theorems must apply. But then the question becomes, what does it mean for a physical system to satisfy the axioms?
Right, like how can you map something concrete onto an abstract axiom system?
The usual answer is isomorphism. We find a correspondence between elements in the physical system and elements in the mathematical structure, so the relationships are preserved. But then critics like Resnick point out that isomorphism itself is a mathematical concept.
So you're using math to explain why math applies to the world. That seems circular.
It does, and this is a problem for any view that rejects Platonism, really. They have to explain how the math they accept can describe a world that's supposedly not fundamentally mathematical.
So what's the deductivist's response?
The entry mentions this idea of a total theory that encompasses all of math and all of science. Within this massive theory, you could maybe explain the connections between mathematical structures and physical situations.
That's a pretty ambitious idea.
It is. But then there's this problem of mixed statements, which the entry calls the Achilles heel of this approach.
Mixed statements.
These are statements that combine mathematical terms, like the number 7, with terms that refer to physical things, like this chair.
Okay, I see. Like, my favorite things are the number 7 and this chair.
Exactly. And for a deductivist, it's not clear how to interpret that whole sentence. You can't read it purely as deduction because it talks about a real chair, but you can't read it literally because it mentions a number which they want to treat as part of a deductive system.
So it's hard to keep the mathematical and the non-mathematical separate in everyday language.
Right. And other non-Platonist views, like fictionalism, run into similar problems. It's really tough to leave the mathematical from the non-mathematical when they're so intertwined in our language.
That makes sense. And finally, we come to the last big challenge. Truth completeness. This one seems connected to Gödel and his pesky incompleteness theorems.
It is. And while the entry mentions that one specific objection about Gödel's sentences might be answered, there's a deeper issue. We tend to think that in areas like arithmetic, every statement is either true or false, even if we don't have a proof yet.
Like Goldbach's conjecture, right? We don't know if it's true or false, but we assume it is one or the other.
Exactly. That's the intuition of truth completeness. But for a deductivist, if you can't prove a statement or its negation, then neither is considered true.
Because truth, for them, means provable.
Right. And Gödel showed that any sufficiently strong system will have these undecidable statements, things you can't prove or disprove. So that clashes with our intuition that those statements must be either true or false.
So how does a deductivist deal with this?
One way is to say that math is ultimately about derivability from some ideal set of axioms that would be complete.
Hmm. That's getting pretty close to structuralism, though, isn't it?
It is. Another way is to change the rules of the game, allowing for infinitary proofs. That also moves away from standard deductivism. And then there's Curry's view, where he basically says that all consistent systems are equally valid and undecidable statements are just neither true nor false within that system.
So he just bites the bullet and rejects truth completeness.
Pretty much. It's a consistent position, but a lot of people aren't comfortable giving up that intuition about math.
So it seems like this truth completeness issue really highlights the problems with focusing solely on proof and derivability.
It does. And it might explain why structuralism, with its focus on the meaning of structures, has become so influential.
Well, that brings us to the end of our deep dive into deductivism. We've gone through the core idea, the historical figures, and the big challenges. And what we've seen is that while deductivism is appealing, it's also very complex and faces some deep philosophical problems.
It definitely forces us to think hard about what math really is and how we know what we know.
So here's a final thought to ponder. After all this, do you still think math is ultimately about provability, about deduction? Or does this idea of underlying structures and their meanings seem more compelling? It's definitely something to keep chewing on. Thanks for joining us on this deep dive. We hope you're leaving a bit more well-informed about the fascinating world of deductivism.